communication, heterogeneous networks, dynamic spectrum access, remote communication, cognitive radio, deep learning for wireless systems, testbed development for 4G, 5G, and 6G wireless, and optimization issues in wireless communication technologies. He has delivered several seminars or webinars on 5G and 5G wireless communications. He has actively worked and contributed to several DST-sponsored projects at GS Sanyal School of Telecommunications, IIT Kharagpur, while during his PhD, and developed the new intercell interference mitigation schemes for broadband wireless access systems. His research work is directly applicable to wireless standards and is useful to mobile operators. He has developed the link and system-level simulators for OFDMA-based wireless networks. He has developed virtual laboratory networks for wireless mobile communications. Dr. Rao has various publications in reputed high-quality journals of IEEE, IET, and WPC. And he has also publications in IEEE flagship conference proceedings, such as ICC. He is an NPTEL team member of IIT Kharagpur. He has around 15 years of post and pre-PhD teaching experience. He has taught various subjects on advanced mobile wireless communications and signal processing areas. Further, he developed the UG new teaching labs on 4G, 5G communications and signal processing, and MTech lab on vehicular communication networks. He has been a reviewer for IEEE transactions on wireless communications, IEEE communications, its letters, IEEE transactions on vehicular technology, IEEE transactions on mobile computing, IEEE access, journal on IET, communications and communications, and a signal journal on wireless personal communications, IEEE conference on communications, IEEE vehicular technology conference, and IEEE MCC. He is a senior member of IEEE, fellow of IETE, and presently he is a member of faculty in the Department of ECE, Electrical and Computer Engineering, Ecole Central School of Engineering, Mahendra University, Hyderabad. We heartily welcome you, sir, Dr. Subbarao Buddu, sir. And I request you to please proceed with the presentation. Thank you, sir.
Yeah, thank you, madam, for that introduction. So, very good morning to the faculty members there and the participants. And so can you enable the action so that I can share my screen? So let me share my screen first.
Yes, sir. Yes, sir.
So I'll go with the, I just switch off my camera so that, it's for the better bandwidth connectivity. So, okay, so I'm just sharing my slides. Yeah, so hope, can you see my screen?
Yes, sir, it's visible and voice is also audible, sir.
Yeah, thank you very much. Okay, so my presentation is mostly on the 5G physical layer structure and the MIMO channel spatial diversity, MIMO channel modeling, and MIMO channel spatial diversity. So the first part of my presentation, I'll talk about the 5G communication. Basically, it's not only on the 5G. So I'll just go with the background first, and I'll take you up to the 6G. Just a brief background about all these generation of the technologies up to 6G, right? Then what are the works going on these the 5G and of course beyond communication systems, right? And then my next part of my presentation, I'll talk about on the MIMO communication, especially on the on MIMO channel modeling and the diversity. It's basically kind of what is the motivation to go to what is the motivation why people are working on this MIMO channel modeling and what is the advantages of this. And more fundamentally, I'll go ahead with, during my second talk of my presentation, my second part of my presentation. Okay, so this, so people are very crazy about, these 5G technologies. When people say that once the 5G comes up, right, it is going to be everything. It's like, we are going to have many in our life, in the sense, in terms of the advancements in the technologies. So we are going to have many advancements in the technologies. Okay, I mean, my first slides talk about the generation of technologies. Right, this is the generation of technologies I kept, right, and what are the services the each generation of technology, each generation supports, and the data rates, you could say the peak data rates, the generation, the each technology supports or each generation supports, right, and what are the waveforms, right, so which are supported by different generation of the technologies. Right, if you see the from the 1G to 2G and 3G and 4G and so on, of course, we are in 5G era, right? We are in 5G because the 5G have been started. I mean, the 5G started using by the people, right? Of course, in India and not fully, not in fullest mode. Maybe it takes 2 more years to deploy the towers and to put the intelligence into the towers, right? And the 6G, of course, it is kind of 10 years from now, or maybe more than that. It's okay because the 6G research is already ongoing. So if you see, there is a 10 years gap between one generation of the technology to another generation. There is a 10 years gap. Okay, so because the research starts, I mean, by the different working groups and the study groups in the industry and academia, right? So it's basically they meet for every 6 months and they release the documents, and the researchers release the documents, right? So especially to name, so we have the 3GPP body and we have the IEEE body, right? So they release the release documents by numbering the documents, that is release 15, release 17, like that. But the latest document is release 17. So just to, I mean, maybe for the researchers who are working on this these areas, I'm just mentioning it. So research 17 is the latest document released, and those who are working on this 5G and beyond, so you can refer to the release 17 document, that is 38.211. I'll go into that. I mean, during my presentation, I'll just show you that, right? So and one more point you should mention, I mean, you should note here is that, so the most important, the waveform that differs when you see the generation, right? Suppose, for example, in 5G, so the waveform is a scalable OFDM, that is the or cyclic prefix OFDM, right? But in 4G also it is OFDM based. Okay, so though there are many proposals on the waveforms like GFDM, that is generalized frequency division multiplexing, UFMC, that is unified filter bank multi-carrier, and generalized. There are other waveforms. People have proposed it, right? People have proposed other waveforms, but the 5G community accepted the OFDM only. So, but there is a difference between the 4G and 5G in terms of the physical layer structure. I mean, the 5-layer start structure. So I mean to say that the waveform is same, that is a OFDMA based in 5G, like in 4G, right? Both are OFDM based, but the 5-layer structure, the physical layer slot structure is different. In 5G, we'll see that in this presentation. And most importantly, I mean, usually the people think, I mean, oh, so the 5G is coming up. So what is so special about the 5G, right? I mean, more technically, what is the difference between the 5G and with its earlier generations? It means that you can say that the connection density, the minimum connection density, that is number of devices you can support per square kilometer by 5G is enormous. It is very huge, right? So that is, you could say 10 lakh devices per square kilometers. 10 lakh devices per square kilometers. Okay, so that is, it's, it is very, very huge number. It means that I would say the connection density is very huge, right? And it's like, not only the connection density, each device needs to be connected. It's like, right, every device, every object, right, is connected, right? Everything gets connected, and that to different services you have to support. It's not only voice, support a video, right? Video streaming, live video streaming, voice, right? Most of these, I mean, all kinds of the services the 5G has to support, right? So that is one, I mean, major point I want to mention here. That is what we call the background about the 5G. And one more point, the among the many technologies, right? The technologies that has a potential, you could say the technologies that will be potentially used to realize the huge demand of throughput and the high quality services which are specified by 5G or specified in 5G, or like the reduction in cell size. I mean, the reduction in cell size, right? That's what I mentioned here. You can say small cells, reduction in the cell size, and the use of massive MIMO. So the massive MIMO we have that is multiple input and multiple output communication. But in massive number of devices are there, so it's going to be massive number of, I mean, the antenna, the multiple input, multiple output antenna communication we are going to use. Of course, we are using in 4G itself, but in the 5G it is use of massive MIMO, which is the one of the technologies. So that will be potentially used to realize the huge demand of throughput and high quality services. So that is one more point one should I mean, remember when you talk about the 5G, and you can also say that the beamforming using massive MIMO. So that is these are the newly developed tools for providing improved service in the 5G mobile standard. That is the beamforming using the massive MIMO. It's not only massive MIMO, but using beamforming. So you will form the beams, right, using the number of antennas, which is basically the antenna signal processing, antenna array signal processing, which is going to which is very critical, and that is very important, because you form the beams, right? The beams will be directed towards the users, right? So it's not simply we say, right, I mean, the beamforming using massive MIMO, but it's basically signal processing, beamforming signal processing using massive MIMO, and small cells, as I mentioned already, and the high frequency bandwidths. So we are going to use the higher frequency bandwidth, that is the millimeter wave. So what you can mention, the millimeter wave communication, that's what wave. Okay, so these are the differences in terms of the technologies, right? Or you can also say, I can also say that these are the technology enablers, right? So when we talk about the 5G, when compared to the 4G communication. Okay, so but once you go to the 6G, it is a bit different, right? I mean, the waveform is what you call the attractive technology. You could say the attractive downlink and uplink transmission scheme waveforms, which we may use, right, or it's expected to be used, is OTFS, that is orthogonal time frequency space waveform, right? So that is going to, I mean, take us into a new direction. So this OTF is usually, we prefer it for a high Doppler scenarios. So I'm not going to talk about in detail. So that is, I mean, of course, I'm not going to talk about this in this session. Okay, we'll see once time comes up. So, and what you observe here is also that what you note here is that the data rates, the generation of technology supports. So once the 1G started in 80s, 70s, 80s time, it is very low rate. Now we are in the TBPS, right? GBPS, of course, we are in GBPS, right? We can download and upload the speeds within just a flash, right? And just less than a 1 minute, I can download a feature film of size 800 MB. Less than, I mean, almost closer to 1 Gbps, I can download within less than 1 minute. So once 5G comes up. But in 4G and 3G, right, it takes in terms of minutes, right? Or you can say 10 minutes or 15 minutes, right? So that is, I mean, the differences between the generation of technologies, and most importantly, the waveform that differs. See, this is a OTFS. It is going to be used in 6G, but in 5G it is OFDM. 4G is based on OFDM. 3G is based on CDMA, and 2G TDMA, and 1G FDMA. Right. So the data rates that are supported by the different generations, it is of course different, right? Of course, we are here now. We are here, right? And what most important you should note here is that the estimation of global mobile subscription is going to be very huge in future, right? So billions of 17.1 billions, right, by 2030. So we are in 2023, right? It is 12.5, right? And the one more difference here is that the small, nowadays we mostly use the smartphones, right? And the usage of the smartphones is very high, right, when compared to the just a feature phones, right, and other smart devices. Okay, it is going to be used, I mean, by the public, I mean, by the humans, right, the tablets and the smartphones when compared to the feature phones. And one more point, you should also note that the machine-to-machine communication is going to increase in future, and in addition to the video, right, non-video is very less, right? Voice calls, you could say non-video is very less, and video and machine-to-machine communication is going to be there in 5G, right? It is so special in the 5G, right? And one more point, what I mentioned is that in 6G, right, the waveform which is expected to be used is the orthogonal time frequency space, right? So there you can see the different dimensions in terms of the signal processing or in terms of the signaling, that is delayed Doppler domain, it will take you. So I'll just brief about it, right? About the OTFS. So in the 6G, right? So you have low Doppler scenarios usually, not only in 6G, usually, right? We have high Doppler scenarios. So we have the high-speed railway communication, right? Drones. We have the communication in the hilly region and vehicular-to-vehicular communication. So in the high Doppler scenarios, the OTFS is especially used. Okay. So the OTFS, if you see that, there are the domains here: Doppler domain and the delay domain. And before that, if you see in OFDM, so we talked about usually the time and frequency. In time and frequency. So, but here it is that time and frequency is mapped to the other domains like Doppler and the delay. Okay. So you can see that different scenarios here. The clutter we have in an area, we have the drones you have, right? You have we have the low Doppler scenarios, high Doppler scenarios, but OTFS especially is attractive for high Doppler scenarios. Okay, so I just wanted to mention these points to you. So maybe maybe some of you may like to work on this area. That's why I'm just giving a kind of a light time on this. Okay, and in OTFS, most importantly, is that so we have the two type of domains, right? See, if time and frequency domain and a delayed Doppler domain, right? So in a delayed Doppler domain, right, we have the ISFFT, that is inverse symplectic FFT, right? And in between we have the Heisenberg transform, Wigner transform. Okay, so once again, I'm not going to the details of it. So this may be trigger, this may trigger the new researchers' mind that, right? Why the OTFS is so important. Okay, we know the phosphorus transform, right? You know the DFT, we know the phosphorus transforms, but here the SFFT, that is symplectic and inverse symplectic transforms, which converts the time frequency domain into delayed Doppler domain. I'm sorry, the delayed Doppler domain to time frequency domain. Again, time frequency, this domain to the time domain, right? And this goes into the channel. Then this time domain to the time frequency domain, then delayed Doppler domain. So it means that my input is delayed Doppler domain and output is also delayed Doppler domain in OTFS waveforms. Okay, so once again, this is very important topic for the researchers who are going to work on this area. It's like this in the time frequency domain, right? The channel looks like this, and in a delayed Doppler domain, the channel looks like this. Means, see the channel gain here, it is channel gain, right? Both are 3D figures, 3D pictures. So, but the axis is different. Frequency and time axis here, it is delay and a Doppler, right? So don't think that the channel is same, right? Channel it doesn't be, but it doesn't change. It means that we are viewing the channel in a other domain. So in a delay and Doppler domain. So Doppler in the sense what? The user velocity of the user. The mobility brings the right. So Doppler into the series system, right? So and the delay. This is another domain, that is the delay, right? So it is basically from the multipath scattering of the multipath phenomenon, right? Because once the waveform is sent, or if you launch an impulse, right, that will go hit an object and comes to the receiver. Likewise, we have many rays. There are multiple reflections. In a multipath fading scenarios, right? The waves, right, or the rays reflected through different scatters in the scenarios, right? So we analyze this for a larger delays and smaller delays, because the waves takes different times, right? So some waves take less amount of time, some waves take high amount of time to reach the receiver. So that's why the delay, right? If you're right, that is what the delay means. So for low delays and high delays, you experience, you'll study how the channel is experienced at the receiver side, and for a Doppler also. So for low Doppler and high Doppler scenarios. Okay, for low Doppler spreads. So see, the channel is different actually. Here the channel is different. There are the peaks here, but this channel is, you could say, time frequency domain. If you see in the time frequency domain, how the channel is varying, like we have the flatness and the low valleys and peaks, right? But here it is mostly, right, the flat many places, but we have the pillars, right? So this is very interesting point in the delayed Doppler domain. If you study the channel, if you understand this, so you are mostly done with the OTFS, right? You can propose many signal processing algorithms, many methods, many schemes in the 6G communication I'm talking about. Okay, so I'm talking about this one. Okay. So by these transforms, right, we can convert this time frequency domain to the delayed Doppler domain. That is right. Symplectic fast Fourier transform. This is inverse symplectic fast Fourier transforms. So once again, I mean, I'm not going into the details of it, right, mathematically. So I'm just giving a kind of light on this. Those, I mean, maybe this could be useful to the faculty or the people who are working on this or who would like to work on this. Okay. So fine. So once again, the 5G potential realizations are like this. Just to name, right? We have the once the 5G is deployed, right? We are going to experience the remote surgery, right? Where which comes under the critical communication aspect, that is ultra reliable low latency communication. So the example is remote surgery and the industrial applications where the robotic assembly, right? I mean, robotic assembly is overseen by the human. So we will have the touch and feel experience, right? And we are going to have the home broadband. So that is wire-free home with the broadband multimedia services in a smart homes is not far away, right? Once the 5G comes up, drones, right? You could say different dimensions. I mean, the 5G takes on and the different services and the different scenarios, right? So we are going to have the virtual reality, drones, self-driving cars, all these. So, okay, so these are the 5G supporting scenarios, right? And in 5G supporting scenarios, especially the enhanced mobile broadband, right? It means that just with 5G wireless communication, you are going to have speeds like fiber at a much lower cost, right? And you are going to have the massive IoT, right? So this is what actually nowadays, right? We think when even think of the IoT, right? Because this everywhere everything is connected, every object is connected, but it's massive IoT. That's what the number of devices are connected, right? So once you in a per square kilometers, what I said is that in my first slide, right? I said that 10 lakh devices, that is the minimum connection density that is supported by the 5G. It's not easy. So okay. So once once that the minimum connection density supported by the 5G means, so using what, right? I mean, how it supports that, right? What are the technology enablers? So what are the technology drivers? So what is the 5G 5-layer technology? What is the MAC layer technology, right? So these two 5-layer and MAC layer technologies play a crucial role in supporting this huge connection density, that is 10 lakh devices per square kilometers, as I mentioned. Okay, and the mission critical control applications, right? So which is going to be another use case in the 5G. And most importantly, in a 5G new radio, so we have the different frequencies. One has already, noted down, that is sub 6 gigahertz band and 6 gigahertz. That is less than 6 gigahertz and more than 6 gigahertz, of course, up to 100 gigahertz. So once you go into the gigahertz band, then we talk about the millimeter wave communication, right? Where our modulation schemes would be different usually, right? Then I'll talk about it later. So, and these are the three use cases of 5G. So, which are enhanced mobile broadband and ultra reliable low latency communications and massive machine type communications. Okay. So these are the three use cases of 5G. And the system requirements of 5G. These are the 5G system requirements. That is user experience data rate, spectrum efficiency, which is 3 times when compared to the 4G, right? And user experience data rate, which is 100, right? I mean, here 100 Mbps, but in 4G it is 10 Mbps, right? And the mobility, right? See the high mobility, it should support high mobility, right? And of course, low mobility as well, right? But compared to 4G, right, the extreme, I mean, the upper limit is 350 kilometers per hour, but in 5G it has to support up to 500 kilometers per hour, right? As I mentioned, right, the OTFS is the waveform which supports this, okay, or which the waveform OTFS which supports this kind of mobilities, and the latency is 1 millisecond. So that is 1 millisecond in 5G, right? But in 4G it is, right, the 10 milliseconds is the latency which is already there, right? And of course the latency, once you talk, right, the user plane latency, control plane latencies are different, right? Of course it captures all those. This latency, right, it captures all those. It's like kind of, you can think of like a round trip latency, which is very less, right, in terms of milliseconds in 5G. And the connection density is, as I mentioned, 10 lakh devices per square kilometer. Network energy efficiency is 100 times more right, when compared to 4G, and area traffic capacity is more. So that is the spectral efficiency per square unit, square area, per square meter, right? It is 10 Mbps you should support, right? So and most importantly, I mean, the new requirements in 5G. So you need to work on this. I mean, you need to understand what is right when in the earlier generation of technologies also, people have worked on this, the peak to average power ratio problem, right? So because we are going to have a low power, I mean, we have more low power and high power devices, of course, but for a low power devices, peak to average power ratio is very critical to work, right? Problem to work on. And the spectrum, you have to understand the spectrum, right? So where we should have the low out of band radiation, should be low out of band radiation, because once you work on the power amplifiers, right? The power amplifiers, since it is the 4G and 5G, these generations, it is based on OFDM. It drives the power amplifiers towards the saturation region sometimes, right? So that time the out of band radiation is a very critical problem to solve. So that's why one needs to understand the out of band radiation. It has to be very low, right? When you talk about the 5G spectrum, right? And in 5G requirements, so enhanced mobile broadband, which is very important, and ultra reliable low latency communication. Okay, so these are some kind of I mean, some of the 5G application scenarios, right, where we'll see the tactile internet services, right? And it's kind of flash time. Tactile internet means what? I mean, your response time is very less, like in terms of 1 millisecond, but I could say like a flash type behavior, right? So, and we have a gigabit wireless, and we have the massive machine type communications, where you can see the low cost devices, right? Very low battery life, right? And we have the a great service you have to see in the crowd, right? So, and most importantly, what I mentioned is that the requirements, when I mentioned about system requirements, so those are all possible by use of the technology drivers or the technology enablers. So which are they using? OFDM, massive MIMO, multi-user massive MIMO, right? And channel coding, that is LDPC channel coding, and the slot structure is different. So you using all these, so I mean, you are going to experience all those. I mean to say, the new system requirements are possible, right? Or you can guarantee that much peak data rate, spectral efficiency, right? And the VoIP capacity. So using all these technology drivers. So just to show you, I mean, just to name a few, and right, NOMA, non-orthogonal multiple access, these are all research areas. Millimeter wave communication, right? And a low latency slot structure device, right? And heterogeneous networks, device to device communication, right? So to meet the goals, right? I mean, 5G uses millimeter wave spectrum, right? And small scales, right? Small cells. So anyway, these are the few technologies, right? Some of the key technologies of the 5G, right? Just for the researchers, I mean, it could be useful. So just as I just read out, so machine to machine communication, massive MIMO, NOMA, device to device, millimeter wave, new waveforms, right? New waveforms. OTFS is, it's a waveform, new waveform, right? Okay. So these are the possible candidate technologies for 5G. These are the possible candidate technologies for 5G, and you should know which technology comes under which layer. So this is under 5 layer, and some are under network layer, some are under the MAC layer, right? So the whatever, I mean, you define the technology, we should see which comes under what layer. Okay, and in this, most importantly, one should understand the releases. Once you talk about the generation of technologies, right? So as we know, the 3GPP body, and that is third generation partnership project, and the IEEE, right? IEEE group, they come up with the proposals, right? I mean, IEEE releases with the documents like IEEE 802 point level something series, but 3GPP releases with the document with the names like LT, long-term evolution, which we are calling it as a 4G standard, right? That is what IMT IMT advanced. IMT advanced is basically 4G, right? So it means that we have we have basically the ITU radio communication sector, right? International Telecommunication Union radio communication sector, which defines the requirements. So to meet the requirements, right? People go with the proposals. So LTE is one kind of a proposal, right? So where the release number is really 8. Release 8 is the number given to the LTE, right? And before that, we have 3G and 3.5G also. That is what 3.5G is HSPA plus. That is high-speed packet access, uplink and downlink, which are given by these numbers. Release 5, release 6, release 7, like that. And now we are, of course, after release 14, release 15, released in June 2018. After that, again, 3 more releases came up by the ITU. That is release 17. We are now in release 17 because what I mean to say is that whoever work on this, the 5G and beyond communications, or of course, forget about beyond, I mean to say 6G. So 5G, who are working on this 5G, 5 and MAC layers, they should refer to this release 17 and release 16, 7, 15, release 15 onwards. They should refer to these documents. Accordingly, they have to work. They have to work on their research, right? So 18 is underway, 17 already released recently, right? So we are working on this actually. Okay. So as I mentioned, right, for these technical specification documents, right, they give the number, specification numbers, right, and each document talks about different things. That is the base station, radio transmission, reception for this new radio, right? You can find that in this 38.104 and fiscal year general description you can find here, right, like that. So now going into the details of the 5G 5-layer waveform, that is the OFDMA base. So you can see that it is based on the 5G it is OFDMA based, right? For the downlink, it is OFDMA, and uplink, it is DFT spread OFDM, that is single carrier FDMA, right? So one should understand how do you define, or how they define the 5G 5-layer structure. Okay, so the 5G 5-layer structure, it is defined like this. So in the layer 1, that is physical layer, it is defined in a bandwidth agnostic way based on the resource block, which is similar to the 4G, right? And allowing the new radio layer 1 to adapt to various spectrum allocations. Adapting, right? We will see what do you mean by this. Adaptive, this is allowing the new radio layer 1 to adapt to various spectrum allocations. Okay, so what do you mean by that? We'll see that in the coming slides. And here the resource block definition is not changed. So that is the resource block. It means that it is the minimum addressable unit in a 4G and in the 5G as well. Means to address a user, maybe a voice user or a video user. I have to define a channel. Like in GSM and 3G, right? We define a channel. We define a channel bandwidth, right? I mean, of course, we name the channel bandwidth this much, right? Maybe 200 kilohertz in GSM. Similarly, in 4G terminology, the resource block is the minimum addressable unit, right? Which takes on a few subcarriers in frequency axis, and in time axis, 14 OFDM symbols. Okay, so the span of 12 subcarriers is at the resource blocks span, right? And the radio frame, it has a duration of 10 milliseconds, so which consists of 10 subframes with a subframe duration of 1 millisecond. Okay, so a radio frame, it has a of course the radio frame it has to usually be shared by the communication, right? Different communication technologies. So radio communication frame, it is defined by the in terms of time duration, right? So it has a duration of 10 milliseconds. Concept 10 subframes means I'm dividing the 10 into again 10 times subframes, and each subframe duration of 1 millisecond. Again, subframe is we can see in the subframe we have the OFDM symbols, OFDM slots, and again in slots we'll see OFDM symbols. So I'll go into the details now, right? So how we can define the all those, the 5G 5-layer structure. So the document structure of 5G physical layer specifications, it is like this. Suppose if you want to know more about physical channels and modulation, you can refer to this document. Multiplexing and channel coding, you have to refer to this document, right? And the physical layer procedure, like for data and control channels, how they are used, how they are defined, you have to refer to these documents. Okay. And what is the modulation scheme, right? What are the coding schemes, right? Are most likely like a link adaptation. So you have to refer to these documents, then you'll be able to understand the details, right? That is 38.211 technical specification documents. This is very, very important. I mean to say that if you want to design a 5G simulator, maybe MATLAB based or Python based or C, right? So to develop a simulator, you need to refer to these documents. That is 38.211. Okay, it means that first you should understand the 5G 5-layer structure, physical layer structure from the slot. I mean, from the physical layer onwards. I mean, how the frame is, how it is defined, how it is divided into subframes, and how the subframe is again divided into in terms of the slots. Again, in the slots, how the WebDM symbols you are sending, because for each WebDM symbols, we transmit the data with using different modulation and coding schemes, different modulation like VPSK, QPSK, QAM, all, right? So this link one should understand. Okay, now going to this, how it is defined, right? This 38.211 document, the 5-layer structure document, how it is defined. So I'm going to the details of it. So that is, I'm going to talk about the frame structure and physical resources, right? So if you see in the time and frequency grade, suppose this time and frequency, right? So the resource element, if you see, right? So what is KL and P mu here? So the first, the fields in the time domain, it is expressed in time units. So we can define it like a TC, right? So where the TC is, we could say the chip time. Okay, so we can define it like this: 1 by delta F max dot NF. Okay, so where NF is the number of subcarriers and delta F max, right? That is a maximum subcarrier bandwidth. So I mean, so those who already know about the OFDM, you know, right? It is basically the kind of subcarrier wise transmission. So right, it is overlapping of subcarriers. You can see in OFDM, right? It is basically right in OFDM we have the subcarriers which are overlapped, right? We just pack the subcarriers. So when you sample this at this time, right, at this sampling instant, the other adjacent subcarriers have the null, right? So that is the basic concept of OFDM, right? In this, the delta F max means maximum subcarrier spacing or subcarrier bandwidth. Okay, for a given system bandwidth, we have the this many number of subcarriers usually defined in a OFDM, right? Of course, here this delta F max is, you can take it like number of subcarriers, right? That is for a given system bandwidth maybe 4096, right? And subcarrier spacing is something like 480 kilohertz. But once again, to tell you here, this 480 kilohertz I'm taking, it is a maximum one, but the 15 kilohertz is the minimum subcarrier spacing that is defined in 4G LTE. Okay, this is fixed. This is fixed 15 kilohertz, but in the 5G, right, in this document, so we have as per the numerology parameter, that is mu here, as per the numerology parameter, right? So it is defined like this: delta F equal to 2 power mu into 15 kilohertz. If mu is 0, so this becomes your 4G OFDM. When mu changes, then your delta F changes, right? So I mean the subcarriers, minimum subcarrier spacing starts from 15 kilohertz, then 30 kilohertz, then 45 kilohertz, 60, it goes like that, 75, 90, and it's as right. It means what is the message here? I mean, what is in terms of physical layer structure? What is different? What is different when compared to 4G is here the subcarrier spacing is different. Subcarrier spacing is varying, right? I mean, subcarrier bandwidth means you are basically varying the subcarrier bandwidth, right? So it is, you are varying like this. Sometimes it is low, sometimes it is high, it is varying. But in 4G, right, it is fixed. See the subcarrier spacing, it is fixed. It is fixed. Okay, so this is one major difference between the 4G and 5G in terms of this, the 5-layer flexible frame structure, right? And once again, so one must understand what do you, all these parameters. Once again, one must understand, right? The OFDM symbol index is L, means suppose if I transmit on that particular symbol, OFDM symbol, right? So that is indicated by L small l, and a small k means the subcarriers index, because see the OFDM is basically the subcarrier wise transmission, subcarrier based transmission. So that's why, right, how it is defined, you must understand. K means for that particular subcarrier and for that particular OFDM symbol, and what is that particular configuration, what is that antenna port, P, antenna port, for antenna port, right? So this is the way the resource element is defined. I mean, so the resource element means what actually here. So if you see in OFDM frame structure, right? So this time wise we have the different OFDM symbols. In frequency we have different subcarriers. So one subcarrier bandwidth and OFDM symbol duration. So that is known as one resource element, RE, right? So I mean one subcarrier bandwidth means 180 kilohertz span this in perpendicularly, I mean vertical direction, and OFDM symbol duration in this direction, right? That is 0.5 milliseconds. So that is called as a resource element, which is basically used for one antenna port. Okay. So and the subcarrier spacing is delta F. Okay. And the this TC and TSR. TC is the basic time unit for this new radio, and the TF is the radio frame duration. TF is the wait, let me show you here. Yeah, here. So we have the TC, basic time unit for new radio, and the radio frame duration is TF. Basic time unit for LTE, right? This is TS. Of course, it is similar for 5G, right? And the subframe duration we have TSF. Slot duration is T slot. Okay, and we have in the subframes we have the slots, right? Number of slots per subframe also we can calculate for the particular configuration parameter mu, right? Or we also call this as a numerology parameter, numerology. So which is defined by understanding this mu. So this is the spacing configuration mu, right? So because see, if I what I mentioned here is that based on the mu, this your entire subcarrier spacing is different, right? Based on the mu, right? That mu you can call it as a numerology parameter in 5G 5-layer structure. So you have to calculate how many number of slots per subframe and how many number of slots per frame for subcarrier spacing for that, right? For the subframe, and this is for frame. Okay, and how many number of symbols for the uplink control channels? How many number of symbols for the number of OFDM symbols? Symbols means here OFDM symbols. Remember, it's not a QAM symbols or modulation symbols I'm talking about. If I mention, right, symbols means you should, I mean, think of what do you mean by symbol. So we have usually OFDM symbols, right, and we have the usual symbols. Symbols means your QAM or your modulation symbols. Maybe you're transmitting your data using QAM, sometimes using BPSK, right? Maybe sometimes using QAM, right? Sometimes you use QPSK, or sometimes you use maybe minimum shift keying, MSK, like this, right? So these symbols are different. OFDM symbols are different. Okay, so please mind that. Okay, so number of symbols per slot, all these, how they have defined and how they calculated, one needs to understand this, right? And now here this TC, that is this chip duration, and the symbol duration. So these are defined like this. This is TC, as I mentioned, right? 1 by delta F max, right, into NF. So what is NF here? Number of subcarriers, right? Number of subcarriers, and the delta F max is maximum subcarrier bandwidth. Okay, and the TS is equal to 1 by reference, delta F reference, right? Means my subcarrier bandwidth, but the reference one is 15 kilohertz, right? The reference subcarrier bandwidth multiplied by the NF, but this is reference, but here it is not reference. I have gone up to max, right? So note down, this is in 5G, right? So reference means this is in 4G, right? So delta F means reference subcarrier bandwidth, reference number of subcarriers, reference subcarriers, right? So here for a given system bandwidth, right? So this is going to be 1 by, let's suppose maximum I have gone up to 480 kilohertz multiplied by this is 4096 for a 20 megahertz system bandwidth. Okay, 480 kilohertz multiplied by the 4096, right? And here it is reference in the sense here it is 15 kilohertz multiplied by reference is here the number of subcarriers reference here it is same for a 20 megahertz it is 2048, right? 2048. These are the number of subcarriers for a 20 megahertz system bandwidth. This is different. Okay, this number is double than this, right? Then if you calculate this 1 by, you'll get around 325.52 microseconds. But here, this one, if you calculate, it would be around, right, 15 nanoseconds. 15 nanoseconds means 1 by 15 nanoseconds. If you do this, this will be equal to 20 megahertz, right? 20 megahertz system bandwidth. It means in a 20 megahertz system bandwidth, right? So the my maximum subcarrier bandwidth is this much, and maximum number of subcarriers are this much, right? So this is TC. Chip duration is this much. My chip duration. 1 by bandwidth, you'll get the chip duration or clock duration. Okay. How you are getting the bandwidth here? Bandwidth is delta F max multiplied by this NF. This is basically your bandwidth. Okay. So 1 by bandwidth will give you TC. Okay, your chip duration. Okay, so these fundamental points one must note. It means that what is the message here is that the subcarrier spacing is variable in 5G, whereas in 4G the subcarrier spacing is fixed. Okay, so as per the numerology parameter, the subcarrier spacing is different here. See, it is increasing. So mu is 0, 2 power 0 into 15, right? It is 15 kilohertz. Mu is 1, 2 power 1 into 15, that is 30, right? So it means the subcarrier spacing is increasing with the value of mu, that is numerology parameter mu, right? So this is the difference. Okay, so it means that what is the message once again here? The subcarrier spacing is controlled by this mu. Controlled by subcarrier spacing is controlled by the subcarrier bandwidth is controlled by the numerology parameter mu. Okay, and of course, if you see in the OFDM symbol duration, we have the useful symbol time and the cyclic prefix. Cyclic prefix duration is controlled by coupled with the mu. Okay, so with the mu, right? I mean, with the numerology parameter mu, we can describe the structure of the OFDM symbol. So we have the in a OFDM symbol, we have the cyclic prefix. We have the useful time, right? So where TU useful symbol time is equal to 1 by delta FSC subcarrier spacing, right? And this total is the OFDM symbol duration. We have the cyclic prefix TCP and a TU here. Together, this is called one OFDM symbol TS. Okay, right? So this entire value of this TS OFDM, right? So OFDM symbol duration, this can change based on the parameter mu, based on this parameter mu. Note down that this mu is not defined in 4G LTE. The mu is defined in this 5G only, 5G physical layer structure, right? And this is coupled with the subcarrier spacing. Okay, so because we have sometimes, when I say the subcarrier spacing is different means we have sometimes narrower subcarriers and wider subcarriers, right? So it means we have the narrower subcarriers, sometimes wider subcarriers, narrow and wider subcarriers. So the subcarrier spacing is different here. I mean, subcarrier bandwidth is different. It is changing. That is depending on the value of this mu, right? The number of resource block also will change because the number of resource block are defined for 12 subcarriers, right? So 12 subcarriers span in a one resource block. We have 12 subcarriers, but here my subcarrier spacing is different. Okay, so it means that each frame has tens of frames, and frame duration is 10 milliseconds. In the 5G file structure, there are 14 OFDM symbols, which is similar to 4G in a slot, which doesn't change with the numerology, right? And number of symbols in the subframe also changes with the numerology here. Number of symbols will change. I'll show you that pictorially so that you'll more, appreciate. So you'll understand. So this is the way that it is defined. Remember, the resource block is not is similar to the 4G. It is not, the definition of the resource block is not changed in 5G, right? Which is, I mean to say, the number of the subcarriers taken or defined in a resource block is same. That is 12, right? And the for a numerology parameter, the number of resource block, it is defined like this, right? For K and L. For the OFDM symbol index and for a particular subcarriers. So K divided by the number of subcarriers in a resource block. That way you'll get the NCRB, right? Common resource block. I mean, So this, suppose if it is, for example, 2048 is your subcarriers and 12 is the number of subcarriers for a resource block, which is this. So you will get the number of resource blocks. That's what n suffix CRB superscript mu means. But it is defined for a particular numerology parameter mu. Okay. So, and you should also note that here this number of these subcarriers, this k, this can be changed based on the application, right? Based on the application scenario, this can be changed, right? So this number can change, but this 12 is same. It is fixed. This won't change. This will change, right? Similar to that, I mean, according to that, this RB changes. Number of resource block will change. Okay, and I should see that here. The bandwidth part is a subset of contiguous resource block for a given numerology in bandwidth part in a given on a given carrier. And here the user equipment can be configured with up to 4 bandwidths. This is what we call the carrier aggregation. It can be configured with up to 4 bandwidth parts in a downlink with a single downlink uplink bandwidth part being the active at a given time. Okay, so this way actually it is defined. I mean, you must also note that here these are all defined. The subcarriers are, I mean, subcarrier bandwidths are defined for both normal and extended cyclic prefix. So the normal prefix, cyclic prefix, and the extended cyclic prefix, right? I mean, the cyclic prefix duration is also coupled with the mu. Cyclic prefix duration, I mean, this one, it is also coupled with the mu. It means if the mu changes, this changes, right? So like this way we can describe, one can describe the structure of the WebDM symbol, right? Using the numerology parameter mu. Okay, or you can say that this TS, WebDM symbol duration TS, this can change based on the mu. Okay, so this choice of this mu and the cyclic prefix CP, right, or this TCP, they're obtained from the from the higher layer parameters, right? So as per the need, right, I mean, things are exploited in the 5G. That is what we mean by the flexibility 5-layer structure in the 5G means. Okay, right. Now, just give me a second. Yeah, so here, as I mentioned, this is the way this slot structure is defined. That is the variable subcarrier bandwidth is defined here. See, for each subcarrier k equal to 0 to, right, it is going up to, right, number of grids for the particular numerology parameter, number of subcarriers per resource block, right? So it is going up to this, right? And this is the way it is defined. What is this? Is basically like, you know, your DFT only. AKL particular symbol for a particular numerology parameter, particular antenna port, and e power j 2 pi k plus k naught, right? All these, right? It's your like a DFT expression, right? So this is all these are captured, right? So this is the way the delta f is defined. Delta f is equal to, right, k times 2 power mu 15 kilohertz, right? So you can write it like this. So where delta f for a particular numerology parameter, delta f mu is equal to 2 power mu into 15 kilohertz, right? So the subcarrier spacing is read like this. Okay, so this is very, very important in especially in the 5G 5-layer structure, one must note. And if you take the numbers here, if you see the numbers here, right? So the mu is increasing, delta f is increasing, OFDM symbol duration 1 by delta f, it is increasing remains, right? So this decreases, this is decreasing. Means what I'm doing here, I am basically changing the OFDM symbol duration. So suppose if this is my useful part and if this is my cyclic prefix part, so I am just varying this. I'm varying, right? If I vary this, obviously this I vary this, right? If I vary this, my subcarrier spacing would vary. Okay, so this is defined for both normal and extended cyclic prefix. See, your CP length is decreasing, right? So this is decreasing TOFDM, right? This is decreasing. So we can see it more pictorially in this slide, right? Like this, see, your frame duration is 10 milliseconds. So this 10 millisecond frame duration is divided into 1 milliseconds, right? 10 subframes. And we have in that number of the subframe duration is 1 millisecond and the number of symbols for the each subframe for a particular numerology parameter means for this particular numerology parameter for mu equal to 0, right? It is 1, and the for 1 it is 2, and mu is 2, then this becomes 4. Okay, so like this, and it means that these are number of waveform symbols in a slot and slots in a subframe, slots in a frame and slots in a subframe, slots in a frame, slots in a subframe, number of symbols in a slot for a particular numerology parameter, right? So for a particular numerology parameter, these values would different. So if you can change that, this is like a 10 times of this, 8 multiplied by 10, 60 multiplied by 10, 4 multiplied by 10, right? And this is for extended cyclic prefix, that is different. Okay, this is for normal cyclic prefix, extended cyclic prefix, it is different. Okay, see if you see that what is this 1 to up to 14? These are 14 WebDM symbols in a slot, right? In a time slot, 14 WebDM symbol. This is not changed. Note down, this is similar in 4G as well, right? So what is changed here is that for a particular numerology parameter, the number of slots in the subframe is different. See, one.
You are muted, sir. Dr. Subbarao, sir, please kindly unmute yourself.
I'm sorry. Yeah, so like this. So we have the number of WebDM symbols per slot, that is 14 WebDM symbols per slot, which is same in 4G standard as well. And what is different here is that number of slots per subframe is different, number of slots per frame is different, number of symbols per slot is same, 14 only, right? But of course, it is defined for different numerology parameters. So like this, suppose if it is for mu equal to 0, suppose first if it is for mu equal to 0, how it is, you can see that for mu equal to 0, it is 14 only because it's 14 multiplied by 1, right? And the next one is for mu equal to 1, it is 14 multiplied by 2, right? Like this means for, and 14 multiplied by 4, that way. Okay. So if you see that, see, this is for the mu 0, right? So it is 66.67 microseconds WebDM symbol duration. Cyclic prefix duration is 4.7 microseconds. And this is the subcarriers, number of subcarriers I have for a given system bandwidth. So this is frequency axis and this is the time axis, right? So WebDM symbol duration, right? How many number of WebDM symbols we have? And these are the subcarriers, right? These are the number of subcarriers. I mean, these are the number of subcarriers. Okay, and if I change the numerology parameter, then so what I am doing here, see, so if I change the numerology parameter, my in frequency wise, my subcarrier spacing is increased, right? So this is T and decrease means, right? So this is increasing. Okay. This is increasing. This is increasing. Okay. So here I'm decreasing the time, right? T, and its cyclic prefix is decreased. This is decreased, right? Of course, if it's decreasing, obviously this will decrease, right? As I mentioned here in the previous slides, right? And note down that the number of subcarriers per a resource block is not changed. It is similar, 12 subcarriers only, right? Number of 12 subcarriers per a resource block is same, right? And as per the numerology parameter, that is mu, my bandwidth allocation is different, right? The number of subcarriers will resource block will change, right? Number of subcarriers will change, right? For different numerology parameters. So if you see this once again, see how it is changed for mu equal to 2, mu equal to 3. So it is varying. So you may think of, so what? So what is the advantage of this? If you see, right, I mean, the if you calculate for a different Doppler scenarios, right? Because this is linked to my communication Doppler scenarios. For different Doppler scenarios, if you vary the subcarrier spacing, right, or the subcarrier bandwidth is increased, so you can change the throughputs, how the throughputs are changing, and even your SNRs are different. Okay, you can do this analysis. So how my signal to noise ratio is varying for different subcarrier bandwidths, right? So you can do that analysis. And if your throughputs will be different for different Doppler velocities, okay, because you have different, you can use these for different services, right, which are used by the 5G. Okay, so this is called the flexible 5-layer structure. Okay, so this was not there in the 4G. Once again, I repeat, this was not there in the 4G. It is defined this way in 5G, so that because in a 5G we are going to have the millimeter wave band. We are going to use, or we use the sub 6 GHz band, right? That is less than 6 GHz band. So sometimes we go for lesser frequency, also 800 MHz band. Sometimes we go for higher frequency and with different services, right? So that way, once you do this, the frame structure, once you do this analysis, right? So you will understand, right, why this is so important. So if you see that, see this one, this is frequency x, this is time. So we have ultra level latency communication. We use this much band and for this much time, and this is we use, right? This is enhanced mobile broadband. This is enhanced mobile broadband, right? This frequency portion we use here for this time, right? Likewise, we have different services scenarios in 5G. Okay, so that's why it is so important. Okay, so as I mentioned here, if you can see for a different Doppler spreads, right? So if you can do this analysis, so it's basically the adaptive subcarrier bandwidth is very attractive, and it is very useful in the 5G. Based on this, of course, it has been accepted in the 5G. I'm saying this research. I mean, I should mention this reference. It is the work done in the Aalborg University by Professor Surashekar Das in IIT Kharagpur. So they have done this in 2014, but they have this idea has been accepted. I mean, this research has been adopted in the 5G, in the 5-layer structure. So this is really a great achievement, right? So once you see how the subcarrier spacing, once you vary the subcarrier spacing, right? How your SNR is varied. The subcarrier bandwidth for different Doppler velocities, Doppler frequencies, and different Doppler velocities, right? It is studied, right? So SNR is increasing, right? Suppose the subcarrier bandwidth is fixed here, right? So here, if you see the low Dopplers, and this is for a little bit high, right? 240 kilometers per hour, right? When the subcarrier spacing, if it is like, for example, 0.3 hertz, my SNR is low, but for a high Doppler, it is SNR is, for low Doppler, SNR is high. But when you vary the subcarrier bandwidth, right? See the SNR, how it is varying. Why do we need to do this? Because we have different type of mobilities, right? You need to analyze your system. Your system should support different Doppler effects, different Doppler scenarios, right? So as I mentioned, right, high Doppler scenarios, OTFS waveform, one needs to analyze. So that's why, I mean, they have done this analysis. If you see that throughput also, right, for different Doppler velocities, when the subcarrier bandwidth is varying, throughput also changes for different velocities, user velocities, right? So this is what you call adaptive subcarrier bandwidth, right? Which has been accepted in 5G, right? So which based on which the different 5G services can be exploited, right? So I would like to stop my presentation now. I'll take a break, then I'll go into the MIMO concept. So because I mean, in my next presentation, I'll highlight about why more fundamentally. So what do you, I mean, what is the motivation for 5G communication? I mean, especially the MIMO communication. So what is the spatial channel characteristics, expression of the MIMO channel, and the diversity. So I'll stop my session here and I'll continue after 5 to 10 minutes.
Okay, so thank you for the presentation. I request all the participants to have a break and rejoin the session after 10 minutes.
Yeah, so I'll rejoin the session after 10 minutes. Thank you very much. I'll rejoin. Okay, I'm leaving the meeting, right?
Okay, sir. Thank you, sir.
Yeah, I'll rejoin. Thank you.